Hello and welcome back to Ordinary Differential Equations, the video series where we talk about the theory of differential equations and what we can do with them. And indeed, in today's part 28, we continue talking about the general concept of systems of linear ODEs. In particular, there we will look at so-called fundamental matrix solutions and the determinants of them. And this specific determinant is known as the Wronski Determinant, or in short just the Wronskian. And at this point I should already tell you that there are a lot of different pronunciations for the mathematician Wronski and the determinant that is named after him. It just depends from which language you come from, and I'm definitely not sure what is actually correct, but I will keep it at Wronski. However, before I formulate the definition of this determinant, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And moreover, as a Steady or Patreon member, you can easily download the additional material for the videos with the link in the description. For example, you find PDF versions, quizzes and books. And then without further ado, let's immediately recall what we mean by a system of linear differential equations. And there you should already know that usually we consider a first order system and write it in an explicit form. So we have the vector x dot on the left hand side and the matrix formula on the right hand side. And in the general form we have the matrix A of t times x plus a vector b of t. So this is the general form of a linear ODE, or more precisely a system of linear ODEs. However, there are some assumptions involved here, namely we want that the two functions a of t and b of t are continuous functions. And moreover, implicitly we also assume that the domain of definition here, called I, is an interval in R. So it could be the whole real number line or just a smaller open or closed interval in R. In fact, the whole thing here is not a complicated ODE at all, and we can just apply our Picard-Lindelof theorem to find global solutions. And we already know the solution set here because it's an n-dimensional affine subspace. This means S is just given by an n-dimensional subspace, which is translated by a solution gamma. So more concretely, gamma here is just a particular solution of our system of ODEs from before. And on the other hand, here S0 is just the n-dimensional solution space of the homogeneous part. Therefore, solving the homogeneous part is the key step in solving the whole system of ODEs. Therefore, you can already remember, in order to define the Wronski determinant, we only have to consider the homogeneous part. However, in contrast to some former videos, here we don't necessarily have an autonomous system. Which also means that we cannot just use the matrix exponential to span the solution space. So more precisely, in the case that the matrix function is a constant function, we can calculate the matrix exponential, and the columns of the matrix exponential span the whole solution space. But still, in the general non-autonomous case, we know that we can find n solutions that span the whole solution space. So we can always formulate S0 as the span of n solutions. This also means that the solutions alpha 1, alpha 2 and so on should be linearly independent. So in the end we are able to choose n functions defined on the interval I. So in the linear algebra language, the functions alpha j are a basis of our solution space S0. However, please don't forget, because we have an n-dimensional system here, every solution alpha j maps into Rn. So in other words, the only thing we need to know here is a basis of the solution space. And now, since we also want to calculate with the solutions, it makes sense to put them into a matrix. So what we get here is a matrix function U that maps I into the space of matrices. Hence, any point in time t is mapped to a square matrix. And now, as already mentioned, the columns of this matrix should have the solutions alpha j. So the first column is just alpha 1, the second alpha 2 and so on. So this is our square matrix and nicely defined for every point t in the interval. And here it might not surprise you that this map is what we call a fundamental matrix solution. So matrix solution is quite clear because it's a matrix and every column is a solution. And on the other hand, the attribute fundamental means that the columns already span the whole solution space. So in fact, this is exactly what the matrix exponential does in the autonomous case. So in that case, e to the power ta is a fundamental matrix solution. Therefore, in the non-autonomous case, this is the natural substitute we have for the matrix exponential. And most importantly, for each t, what we have here is a square matrix, which means we can calculate the determinant of it. And exactly this leads us to the definition of the Wronski determinant. And we assume the same thing as before, which means we have this linear system where a of t is a continuous matrix function. Hence we know, as before, that we definitely find n linearly independent solutions for this system. However, maybe we cannot check, or we don't want to check, the linear independence, which means we just grab any n solutions. And now by putting these in the columns of a matrix, we still get out a matrix solution, but maybe not a fundamental one. So in that sense, it's just more general, but this is what we need in this definition here. Namely, what we do here is to take this square matrix for every t in I, and then we calculate the determinant. And moreover, we also introduce a new symbol for this determinant. We write w of t. And unsurprisingly, this is what we call the Wronski determinant with respect to our ODE and the chosen solutions. So please keep that in mind. The Wronski determinant is not completely fixed because it depends on the solutions you put into the matrix. And moreover, you also often see just Wronskian as an abbreviation for this determinant as well. And now you should immediately see the advantage of this new quantity, because it's just a real valued function, because for every t we get out a real number. And this number can actually tell us if we have a fundamental matrix solution or not. So for example, if we find one t in I where this determinant is non-zero, then we can immediately conclude that the vectors here as functions are linearly independent. Hence, if the Wronski determinant is non-vanishing at one point, we have a fundamental matrix solution. However, it turns out that we even get a stronger claim out when we want to say that we don't have a fundamental matrix solution. And exactly this I want to discuss in the next video, so I really hope I meet you there again, and have a nice day. Bye bye.